So let's review the quantum numbers. The quantum numbers are actually solutions for mathematical equation, and we use this combination of numbers to describe the orbital. And the orbital is this volume in space, right, around the nucleus of an atom where we can find the electron, or we have a high probability of finding an electron. So we have three quantum numbers listed here. Principal quantum number, which is telling you the energy level where you have the electrons. The principal quantum number is related to the periodic table. The periodic table, it's divided in periods, and you have 7 periods, right? Now the energy level, it's given by the period number, or the period number, it's actually telling you in what energy level you're going to have the last electrons that you're placing in a specific electron configuration. The second one, letter L, to represent the angular quantum number. Now, this quantum number is telling you the specific type of orbital that you have. You can get the numerical value of L if we know the numerical value for N. So the value for L is given from for it's a number from 0 all the way to n minus 1. So if, for example, the numerical value for your principal quantum number is 4, you can have three possible values for L, starting at 0, 1, 2, and 3. So the largest value for L that you can have for n equals 4 will be 3, because it goes from 0 all the way to n minus 1. If n is 4, 4 minus 1 is 3. So if you have a numerical value for n that is equal to 2, for example, your values for L are going to be 0 and 1. And 1 is the maximum number that you can get, because if n is 2, 2 minus 1 equals 1. So you have a summary of four principal quantum numbers, and 1 and 2 and 3 and then 4, and all the possible values for L for each one. When n is 1, you can have just one value for L. When n is 2, you can have two values for L. When n is 3, you can have three values for L. And then when n is 4, you can have four values of L, which are 0, 1, 2, and 3. Now, this angular quantum number is telling you the specific type of orbital, because we assign a letter to represent that numerical value. So on the right side, you have a list of numbers for L, and those are the possible values for L that we're going over: 0, 1, 2, 3, and 4. And then the specific type of orbital that you have for each value of L. Whenever you have a numerical value of L equals to 0, the type of orbital is S. When the numerical value of L is 1, the type of orbital is P. When the numerical value of L is 2, the type of orbital is D. And lastly, when the numerical value of L is 3, the type of orbital is F. Now this works also the other way around. Whenever you have an orbital that is a p orbital, the numerical value of L is 1. If you're looking at an orbital that is a d orbital, the numerical value of L is 2. Now the third quantum number is the magnetic quantum number. This one we're using to determine how many orbitals of each type you have. So the possible values that we're getting for this magnetic quantum number are given by the numerical value of L. So if you know the numerical value of L, you can determine the numerical values for n sub L. The values of m sub l, they're going to start at a number that is negative L all the way to positive L passing through 0. So what that means is, if you have a value of L that is equal to 2, since m sub L goes from minus L all the way to plus L, your numerical values of m sub L are going to start in negative 2, negative 1, 0, 1, all the way to 2. So for that specific example where you have L equals 2, I'm getting these 5 possible values of m sub L. 5 possible values means that you have 5 orbitals. Which type of orbital? When L is 2, the type of orbital is d orbital. So these 5 possible values, what that means is that if you have 5 possible values, it's because you can have 5 orbitals of that specific type. So when L is 2, you have 5 possible values of m sub L, and that is related to the number of orbitals that we have for d orbitals. When L is 1, you see the values of m sub L are minus 1, 0, and 1. 3 possible values. 3 possible values means that for that specific type of orbital, you can have 3 of them. So when L is 1, the type of orbital that you have, L1, 3 possible values. Type of orbital is a p orbital. So for p orbitals, you can have 3 of them. For d orbitals, you can have 5 of them. And then for s orbitals are given by your quantum number L equals to 0. When L is 0, the value of m sub L is also 0. There's no negative 0, there's no positive 0, it's just 0. So you have just one possible value. One possible value is telling you that you can have one orbital of that specific type. So you have different energy levels that are given by your principal quantum number n. Then in each energy level, we're going to have sub-levels. Those sub-levels are given by your angular quantum number L. In your principal quantum number, if your principal quantum number is 1, you have one sublevel. That one sublevel is 1s orbital. If your principal quantum number is 2, you have 2 sublevels. Those 2 sublevels are 0 and 1, and that indicates that you have s and p orbitals. When you move to the third energy level, principal quantum number 3, you have 3 sublevels. Those 3 sublevels are given by 3 possible values of L, 0, 1, and 2. And what that means is that you have 3 different types of orbitals, s, p, and d orbitals. How many for each one? Whenever you have s orbitals, it's just one of them. So you can have an s orbital, one of them in the first, second, third, fourth energy level. When you have p orbitals starting in energy level 2, second energy level, p orbitals, you're going to have 3 of them on the second, on the third, on the fourth, on the fifth, and so on. On the third energy level, you have 3 sublevels. three sublevels given by your quantum number L, 0, 1, and 2. So you have three sublevels, three different types of orbitals, S, P, and D orbitals. The set of quantum numbers N, L, M sub L is going to be used to describe one orbital. Now, we don't have two electrons with the same set of quantum numbers. Remember, the quantum numbers are giving you an idea of where the electron is located. You cannot have two electrons in exactly the same location. Electrons are negative charges. If you try to push two of them close to each other, they're going to repel. Okay, the same charge will repel. So you cannot describe two different electrons with the same set of quantum numbers because that does not make any physical sense. So if we have three quantum numbers so far, N, L, and M sub L, we can use those three quantum numbers to specify an orbital, but not two electrons in the same orbital. To specify a set of quantum number for two electrons sharing the same orbital, we're going to need a fourth quantum number. The fourth quantum number is M sub S, and that's the spin quantum number. That spin quantum number is just to give us an idea of the orientation of an electron. So let me give you some examples here. I have hydrogen and helium. Electron configuration for both. Hydrogen, 1 electron, 1s1. Helium, 2 electrons, 1s2. So I have my representation here using the half arrow pointing up for 1 electron, pointing up for 1 electron in helium, pointing down for the second one. So I'm going to write down my quantum numbers and L, M sub L for hydrogen. If your electron in hydrogen, look at the electron configuration, 1s1. That 1 is telling you that that electron in hydrogen is in the first energy level. So 1 indicates the energy level. The energy level is the same as your principal quantum number n. So that electron in hydrogen, which is in the 1s orbital, principal quantum number is equal to 1. That electron for hydrogen. And when I'm saying electron, I mean this electron right here. It's in the first energy level in an s orbital. When you have an s orbital, the s orbital is an s orbital because the value of L is 0. Remember, L equals 0, s orbital. L equals 1, p orbital. L equals 2, d orbitals. So s means that the value of L is 0. The value of M sub L, if L is 0, M sub L is also 0. So now I have three quantum numbers describing my electron in hydrogen. If we look at helium now, and I'm going to write down the same thing twice because we have two electrons in helium. One is 2. The 1 is telling you the principal quantum number. Those two electrons for helium are in the first energy level. So that's 1 for N. Those two electrons for helium are in an s orbital. If it's an s orbital, it is an s orbital because the value of L is equal to 0. If L is 0, m sub L is 0. Now I'm going to check my second electron, the one that I have in blue. The second electron in helium is in a 1s orbital, the s orbital in the first energy level. So the principal quantum number is still given by that 1, which is the first energy level. The value of L, you have an s orbital. If it's an s orbital, it is an s orbital because the value of L is 0. If the value of L is 0, the value of m sub L is 0. So you can see here that I'm describing two different electrons. It's two different electrons for helium, and I'm using exactly the same set of quantum numbers for both of them. These two sets that I'm writing down are a set of quantum numbers that I can use to describe the orbital. But to specify which electron is it, the one that I'm writing the quantum numbers for, we need to write down the last quantum number. Now these three here, that's okay. This is describing the orbital. Okay, I have an s orbital in the first energy level. That's fine. But in that orbital, we have two electrons. We cannot describe those two electrons with the same set of quantum numbers because that means that they are exactly in the same location at a specific time, and that is not physically possible. So this fourth quantum number here, it has just two possible values, plus 1/2 or minus 1/2. Remember, this is just to indicate the orientation, and this is a very simplification of what's happening. Okay, so you have two electrons, and let's say that you're looking at a sphere, right? It means that your two electrons are going to be in a opposite direction. So one is going to be pointing on one side and the other one on the opposite side. Maximum amount of space between them to avoid your repulsions. So whenever you have two electrons in a same orbital, the first electron that we place, the one that I have pointing up, will have an ms value equal to +1. The electron that is pointing down will have an ms value equal to -1/2. Now you don't have four quantum numbers that are equal for two different electrons, right? You have three of them that are the same, and that will always be like that because those two electrons are sharing the same orbital. So we can actually describe the orbital with those three first quantum numbers. Now, the last quantum number is just to specify that you have two different electrons in that orbital, plus 1/2 minus 1/2. Plus 1/2 for the first electron that is being placed in the orbital, minus 1/2 for the second one. So, just to practice, to add your fourth quantum number here for hydrogen, you have just one electron for hydrogen, right? The one that is pointing up. So if your electron is pointing up, that value for m sub s will be positive 1/2. So I have here two examples. For the first one, you have Cl, atomic number 17, you have the electron configuration, and I'm giving you the electron configuration right here, showing you all the electrons in the orbitals. So what I want you to do is to write down your set of quantum numbers, all four of them, for this specific electron right here. So for that last electron in your electron configuration for Cl, write down the four values for N, L, M sub L, and M sub S, all four. Now, for M sub L here, you're going to have more than one possible value, and that it's possible. You can have more than one possible value for M sub L. You have only one possible value for M sub L when L is 0, but whenever L is different from 0, you will have more than one. And now, the last thing for the second one is the ion of Cl with a charge of -1. So for Cl you have 17 electrons. For Cl-1 you have 18 electrons. So the electron configuration for Cl-1 is not 3p5. It will be 3p6 because it's gaining one electron. And I want you to write me the four quantum numbers for that last electron. The one that is added when Cl is gaining one electron. So you have the ion. So write me the four quantum numbers for that last one.